All right, greetings YouTube. Beautiful mind here. This question comes in from that same section that we just did. I forget the question number, but I think it's 2.5 from Applied Statistics. This question has the following. It says a certain brand of automobile tire has an average lifespan of 40,000 miles and a standard deviation of 2,000 miles. Assume the lifespan of the tires have a bell-shaped distribution. Part A says the standard score, or the z-score, represents the number of standard deviation a given x value falls from the average. So we're asked to find the z-score that corresponds to each lifespan. So the formula is actually given right there. And so the z-score, what it is, that's another way of articulating the standard deviation. What it is that we have this data that where the data is kind of displayed in like a bell-shaped curve as far as how it's spread out. So the average is in the center, and then what we're doing is standardizing the data. So instead of our average being whatever the number is, we're pretty much setting the average to be 0. So 0 being in the center, being our average of the bell-shaped curve, that's going to represent like the middle of the data. If a data entry has a positive z-score, then it's going to be to the right of our average, and it's going to go to the right side of the bell-shaped curve. If our data has a negative z-score, that just means it goes to the left of our average or to the left of the center of our bell-shaped curve. So that's all that the z-score is doing. It's just standardizing the average so that now the average is essentially set to 0. And then if it's positive, that means the number's going to the right. If it's negative, the number's going to the left of the average. So we could find the z-score of each of these. Let me see. Where is the data? Okay, so we have it's essentially here. It's nothing. It's not difficult here, right? So we're actually use this formula to find the z-score. So the data that we have, it says for the lifespan of 36,000, the z-score is -2. So basically, they gave us the average, our mu. It says that it has an average of 40,000 miles. So if we did the 36,000, which is a data point that's given, minus the 40,000 divided by the standard deviation of 2,000, we'll get -2. If we plug this in, 39 minus 40 divided by the 2,000, we get a -0.5, and 30 minus 40 divided by 2,000 gives us a -5. Okay, so all of these are to the left of our mu, or our average, right? So again, the z-score is similar to the standard deviation. It just tells us how far away from the average we are. Okay. So then for percentile, so there's another part in the text that says something in the following nature. It's the empirical rule. So whenever our data is normally distributed or kind of exhibits a bell-shaped curve, there's I think it's 68, 95, 99. It's called the empirical rule. So if you kind of scroll through the text, you'll see it. And I think we talked about it in the notes. So say our data has a bell-shaped curve, something like this, right? So say this is our average. We're going to say this is our mu, or the average. And then the empirical rule says that, let me see, say this is one standard deviation about here. And then, let me see, so this is, sigma? So this is mu plus 1 standard deviation. This is going to be mu minus 1 standard deviation. And then say we have a second standard deviation there and about there. So the empirical rule says that about 68% of the data is in the center. Let's just do that one as orange. So 68%, when the data is displayed in a bell-shaped curve, 68% of the data is going to be here, within 1 standard deviation of the center. Right? That's called the empirical rule. And again, that implies whenever our data has exhibits a bell-shaped curve. And these are all approximations, right? So 68% of the data is going to be here, within plus or minus 1 standard deviation from the average. And then the next part says that, let's do it like this. about 95% of the data is going to be plus or minus 2 standard deviations from the average. So that one, along with this one. So the orange plus the green is going to be about, what do we say, 95% of the data. So we're going to say this is about 95% of our data is going to pretty much going to be encapsulated from here to here. All of this is going to be 95. And then when we go about 3 standard deviations out, let's just make that one this one. And let's put this back real quick. So then say we're like something like here. This is going to be, this was mu plus 2 standard deviations. This was mu minus 2 standard deviations. And then if we said mu plus 3 standard deviations and something like out here, mu minus 3 standard deviations, that's going to encompass about 99.7% of the data. So this is going to be 99.7% of the data. It's going to fall from, it's going to basically go from here within plus or minus 3 standard deviations. Okay. So then, so it's essentially something like this, as far as the empirical rule. So this is in your text. I would look in this section to get the details, but this is the gist of it. So then, so it says find the percents of the distribution of the area that is situated to the left of each given value. So if we have, so for a lifespan of 38,000, the z-score was -1, right? So when we put these into terms of z-score, this is going to have a z-score of 0. This is going to have a z-score of -1, right? So if this is 68, if the orange is 68, half of that is what, 34%? So this region over here is 34%. This is also 34%. Let's get that to be a 4. 34%, right? So if we're going to the left, if we have a z-score of -1, that means basically we're talking about what percent is to the left, right? So then, let me see. If that's 95 and we use 68, what's 95 minus 68? 25, 28. And then 28 divided by 2 is what, 14? 28? Yeah. So this is about 14% of the data here. This over here is also about 14% of the data, all right? So now if we've used 95%, what's remaining is 4.7. So say that was 4.6, 2.35. So then, as long as I'm doing this proper, this should be about 2.35% of the data, and I think this one is also 2.35% of the data, right? So if we're here at a z-score of -1, that means basically we got to say this purple plus this green to give us, what is that, 16.35% of the data? 16th or 17th percentile. 16th, you see it right there. So remember we said that the 2.35 plus the 14 was approximately 16.35. You see, so that's going to fall into the 16th percentile. Let's do the 42. The 40, oh, wait a minute. Why did we get negatives? Did I do something wrong there? The z-score, 30,000, okay, 40,000. Okay, so maybe they just gave us some different data. Okay, we're fine. So if we say the z-score corresponding to 42,000 was a positive 1, so a z-score of a positive 1 is actually, not that one, is here. Here's a z-score of positive 1. So this is z equals 0, this is z equals -1, this is z equals 1, right? So a z-score of positive 1, so basically we have to add the 34 plus the 34 plus the 14 plus the 2.35. So this is 68%, 68, 78, 82, 84.35. So that's going to be 84th percentile. You see it right there. And then if it's 40,000 and it has a z-score of 0, which is in the center, right here, z-score is 0, that's the middle. So these should add up to about 50%, right? 34 plus 14, you see 34, 44, 48, 50.35. So these add up to approximately 50%, and that's why it's the 50th percentile. Hopefully that made sense. But that question was just asking you to basically read the chart for the empirical rule. That's all it was really trying to get you to do. So this definitely comes from that section. I will open up the text for the second part. Again, the z-score, all we're doing is taking the average and we're normalizing it so that now the average is going to be 0. If our z-score is positive, that means our data is falling to the right of the z-score. If our z-score is negative, that means our data is falling to the left of the z-score. Okay. So hopefully you were able to use that. My previous video is actually still loading, so it'll, once it's loaded, I'll just go ahead and load this one as well. And on that note, we're going to end this session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.